Up until now, we've been looking at just gravitational fields and the forces they can create, called gravitational forces. But we're going to start looking at other types of fields too. And the next type of field I want to look at, largely because it has a lot of similarities to gravitational fields, is electric fields. And I want to start this discussion by thinking about some of the properties that matter has. So matter is made up of little particles. And we learn early on in high school that those particles are called atoms, and those can actually themselves be said to be made up of little particles called protons, neutrons, and electrons. And one property that protons, neutrons, and electrons all have is mass. Protons and neutrons have a fair bit of mass, electrons have a tiny bit of mass, but they all have some mass. Therefore, they would all create gravitational fields. Now, another property that all of those particles have is charge, electric charge. So not only is all matter made up of particles that have mass, all matter is made up of particles that have charge. And so this leads us from a discussion on gravitational fields into a discussion on electric fields, which are created by charge. So matter is made up of particles which are positively or negatively charged. Now, so positively charged would be a proton, negatively charged would be an electron, and we should point out there is a third option here. They could also be neutral, meaning no charge, and that would be our neutron. Now, up until now, any talk you've done about electric charges, especially if we're talking about subatomic particles, has probably avoided using units. You would likely have heard that protons have a charge of +1, electrons have a charge of -1, and neutrons have a charge of 0, without really assigning a unit to that amount of charge. In this course, we're going to start dealing with much larger quantities of charge. Instead of just looking at a single proton or a single electron or a few of each, we're going to look at things that might have millions of protons or millions of electrons in them. So we're going to use a different unit for charge, and that unit is called the Coulomb. Coulomb has a capital C because it's someone's last name, and the short form of it is going to be just a capital C. And we'll talk about exactly how much a Coulomb is in just a moment. Another thing we should note about charges is that they are conserved. There are a few things in our universe that seem to be conserved. Mass seems to be conserved. In a chemistry course you've taken, you've probably talked about conservation of mass, especially in the context of balancing chemical equations. Energy is also conserved. In physics, you'll have talked about the law of conservation of energy, how energy can't be created or destroyed. In physics, you'll also likely have talked about how momentum is conserved. Momentum can't be created or destroyed. Well, now we have another thing that's conserved. Electric charge is conserved. Electric charges cannot be created or destroyed. In fact, it's thought the total charge of the entire universe is constant and neutral. It basically means that when the universe was created at the Big Bang, there were some, shortly after that, there were some neutral charges that were created, and some positive charges and some negative charges. Those positive and negative charges would have had to totally balance each other out, giving us a total neutral charge, and it's remained that way ever since. Another important thing about charges is that they are quantized. meaning they occur in packages. Now, some things we measure are quantized, some things aren't. Length is an example of something that isn't really quantized. If I want to measure the length of something, it can basically always get smaller. And I can measure, the length of a ruler. It's pretty big. I could measure the length of an atom from one side to the other. That's a bit smaller. I could measure the length of an electron from one side to the other. That's even smaller. But as I find smaller and smaller things, length can always get smaller and smaller. Mass is something that can't always get smaller and smaller. Basically, the smallest thing we can have that has mass is a proton or a neutron. And I can't really break those up into smaller pieces that have mass on their own. So basically, if you want to know how much mass is in something, you're basically counting how many protons and neutrons it has. The smallest amount of mass I can have is the mass from one proton or one neutron. This is also especially true about charge. The smallest amount of positive charge I can have is the charge of one proton. If I cut a proton in half, we can sort of break a proton apart into pieces. There are sort of smaller particles that make up protons, but it's not like each of them would have half the charge of a proton. If I break a proton up, it sort of stops having charge at all. So there's no way to have an object that has half the charge of a proton or half the mass of a proton. So that's what we mean when we say it's quantized. Charge occurs in packages. The positive package is one proton, the negative package is one electron, and I can have multiple packages, but I can't have half of a package or a fraction of one of those packages. So the charge in one of these packages is the smallest amount of charge we can have, and we call it the elementary charge. This is the charge on one proton and on one electron. If it's the charge on a proton, it's positive. If it's the charge on an electron, it's negative. And this charge, because it's so important, it's given its own letter. It's given the letter E. E for elementary charge. And it has a value of 1.60 times 10 to the negative 19 coulombs. That is the amount of charge on one proton, if we're talking positive charge, and it's the amount of charge on one electron, if we're talking a negative charge. Now, this guy called Coulomb determined that if I have a couple of things that have charge on them, there will be a force between them. And that force is proportional to the charges. So the more charge we have, the more force there is. And it's inversely proportional to the square of the distance between them. Meaning the more the distance between them, the less the force will be. And something's getting squared there. This became known as Coulomb's law. And in formula form, it looks like this. So let's talk about some of the things in this formula. Q1 is the charge on one object. And it'll be measured in units of coulombs. Q2 is the charge on the other object. And it's also going to be measured in coulombs. R is the distance between the objects. It's going to be in meters. And K is called Coulomb's constant. And being a constant, it has one value, and that value is 9.00. This is an easy one to remember, I find. Times 10 to the 9. 9 times 10 to the 9. And we can sort of isolate K in this equation, move everything to the other side, figure out what the units of K would be, and we get Newton meters squared per Coulomb squared. And there are other ways we can write these units as well. Now, looking at this formula, it's probably looking a little familiar, and that's because it looks very similar to Newton's universal law of gravitation, which was Fg equals m1, m2, big G over r squared. So let's look at the similarities. In Newton's universal law of gravitation, it tells me about the force between two objects with mass. Here are the masses of those two objects. In Coulomb's law, it tells me about the force between two objects with charge. Here are the charges of those two objects. Now, in Newton's universal law of gravitation, that force depends on the distance between the centers of gravity of the two objects. And in Coulomb's law, the force depends on, I guess we could call this the distance between the centers of charge of the two objects. I've just said it's the distance between the objects, sort of simplified things a bit. And the reason for that is we tend to use Newton's universal law of gravitation with objects that are quite big and have a noticeable shape and take up a lot of space. So the outside of the object, the surface, might be very different from where the center of gravity is. However, with Coulomb's law, we tend to use it a lot more often with objects that are really, really small, something like a proton or an electron, where it doesn't really take up much space. We call these things point charges, meaning they're so small we can basically consider them to be a dot. They exist at a single point and nowhere else. So for that reason, we don't necessarily have to talk about this R as being between the center of charge of one object and the center of charge of another. We just say it's the distance from this object to the other, from one dot to another, and it's pretty obvious what that distance is. But if we were to use this law with really big objects that had a lot of charge on them, although those things rarely exist, this would be the distance between their centers of charge. And the last thing I want to kind of compare between these two formulas is big G, the universal gravitational constant, and K, Coulomb's constant. I usually say that big G is sort of like a number that says how strong gravity is in our universe compared to all the other forces. Similarly, Coulomb's constant, K, is a number that says how strong electrostatic forces are in our universe compared to all the other forces. Now, big G is a really small number. right? It's on the order of 10 to the negative 11. K, you'll notice, is a really big number. It's on the order of 10 to the positive 9. So that tells us that while gravitational forces are really weak in our universe, electrostatic forces are really big. Electrostatic forces are much, much stronger than gravitational forces. Sort of an example of that is it's not really hard in a room, like a classroom, to come up with a scenario where you can give objects some electric charge and use them to pull each other around, right? You take a balloon and rub it on your head, it gets a bit of charge, and you can stick it to a wall, or you can use it to attract other balloons. It can pull your hair towards it. So it's pretty easy to create an electrostatic force that'll pull things around for you. But doing that with gravity is hard. Trying to get a balloon to stick to the wall simply by the gravitational force between them is impossible. Trying to get a balloon to attract some of your hair towards it simply because of the gravitational force between your hair and the balloon, not going to happen. Basically, the only gravitational force you're likely to ever notice is that coming from the Earth, because the Earth is so huge, it makes up for the fact that gravity is such a weak force. But with electrostatic forces, because K is so big, the charges don't actually have to be that big for us to notice this force. So a few notes I want to add on electrostatic forces. First of all, as I've just mentioned, but let's write this down, electrostatic forces are way bigger than gravitational forces. Let's say way stronger. And that's because K, Coulomb's constant, is way bigger than G, the universal gravitational constant. The second thing I want to note about electrostatic forces, by the way, I keep using this word electrostatic forces. Electro means it's coming from objects that have electric charge, and static just means those objects aren't moving. So if I have a proton sitting on a table and an electron sitting on a table, they're both static and they're both electrically charged. So there will be an electrostatic force between them. The other type of electric force is you could call it an electrodynamic force, where maybe I have a proton and a neutron and an electron, so they both have electric charge, but one of them is moving. So instead of that charge being from something static, that force being from a static charge, the force is coming from a moving charge. Once we consider charges that are moving, the forces get a bit more complicated. So we're starting simple. We're starting with things that have electric charge and are not moving, which means they are electrostatic forces. So electrostatic forces can attract or repel. And by attract, I mean pull. And by repel, I mean push. So a charged object can pull each other or they can push each other. Pull happens when they are opposite charges or opposite polarity. Polarity is a word that refers to not the amount of charge, but just whether it's positive or negative. So a positive charge and a negative charge those have opposite polarity, so they will attract each other. We often say like charges, or charges that have the same polarity, will repel each other or push. So two protons have the same polarity, both positive, so they'll repel. Two electrons have the same polarity, both negative, so they'll repel. Gravity in contrast, can only attract. There's no way for two objects with mass to repel each other through the force of gravity. Gravity can only pull. So as much as there are some similarities between electrostatic forces and gravitational forces, there are some differences as well. And this idea of attracting and repelling is one of those. Now, the last thing I want to say about this formula, Coulomb's law, is it does not tell us the direction of the force. Notice there are no vector hats anywhere in this formula, even though force is a vector. There are no vector hats in this equation. And the reason I've done that is because this equation will not tell you the whole story. This equation will tell you the magnitude of the force, but the direction of the force, you need to find out on your own. So what that means is don't use plus and minus signs when you sub numbers into this equation. If Q1 has a positive polarity, don't make a point of writing a positive sign beside that charge. If Q2 has a negative polarity, don't make this a negative number when you plug it in. Just plug in the amounts, right? Everything positive, and you'll get a positive number for F, and that tells you the magnitude of the force. The direction, you figure out on your own. And you can do that using the knowledge you have that opposite charges will attract and like charges will repel. So let's move on and look at a couple of examples now. First of all, I'm just going to label our new formula, Coulomb's law. Okay, 2 point charges of 1.8 times 10 to the negative 6 coulombs and 2.4 times 10 to the negative 6 coulombs produce a force of 2.2 times 10 to the negative 3 newtons on each other. How far apart are these two charges? So this is basically just some pretty simple plug and play. I'm given two charges. I'm not explicitly told if they're positive or negative. So that means it's going to be hard to tell if this is an attractive force or repulsive force. But I don't think I really need to know that for this question. Either they'll be attracting or repelling each other. If they're attracting with this force. If they're repelling with that same force. And I just need to figure out how far apart they are. So we can use Coulomb's law to do this. F equals K Q1 Q2 over R squared. In this question, we're asked how far apart the two charges are, meaning we're looking for R. So let's rearrange this formula to isolate R. So I'm going to move R over to the left-hand side and bring it up to the numerator. And then I'll move F over to the right-hand side, and it'll go down to the denominator. And I can just sort of square root both sides. And we can plug some numbers in. So K is 9 times 10 to the 9. Q1, just like with the universal law of gravitation, it does not matter which charge is Q1 and which charge is Q2. So this can be Q1 or Q2. This can be Q1 or Q2. I guess we've kind of in this course settled on a convention where the larger charge is Q2. So if you really want to pick one specifically, we can go that way. But it really doesn't matter. Okay, so if I crunch those numbers, I should get, somewhat surprisingly, a pretty normal looking number. 4.20. Kind of rare that you have a situation like that where everything here is in scientific notation with big exponents and we just get a pretty normal looking decimal in the number of ones. So we should just check units. Again, standard procedure that I like to go with is I just make sure I've got metric base units going in, then I know I've got metric base units coming out. So that's the standard number for K. It's in metric base units. The two charges I used were in coulombs and coulombs. That's metric base units for charge. The force number I used was in newtons. That's metric base units. So because I had all metric base units going in, I know I'm going to get metric base units out. So this value I got for R is going to be in meters. Okay, let's look at this next problem. I've got 3 charges that are placed all in a row here, and they're a few different distances from each other. I've got my 1.7 microcoulomb charge and my 2.5 microcoulomb charge. Remember, 10 to the negative 6 has the prefix micro. That's these two charges here. And it says they are a distance of this apart. 2 times 10 to the negative 2 meters, or 2 centimeters. So let's add that into this diagram. These guys are 0.02 meters apart. And then it also says my 1.7 microcoulomb charge is 3.5 centimeters from a 2 microcoulomb charge, or negative 2 microcoulombs. That's this charge over here. So let's add that distance into this as well. The distance from this guy to that guy is 3.5 centimeters. Now we want to know what is the net electric force on the 1.7 microcoulomb charge on this guy. So it's feeling a couple of forces. One from this object and one from this object. We're going to add those forces together to find out what the net force is. So, quick free body diagram for the object we're interested in. There's my 1.7 times 10 to the negative 6 Coulomb charge. So this guy is positive, and this guy is positive. So those charges have like polarities. They have the same polarity. They're both positive. So we know that like charges repel. So they're going to be trying to push each other apart, which means my charge that I'm focusing on over here is going to feel a push to the left side of my page. Now let's look at the force that my charge feels from the other charge. Here I have a positive charge and a negative charge, so they have opposite polarity, one positive, one negative. And that means they're going to attract. So they will be pulling on each other. And that's going to make my charge feel a force to the right. Now, in my free body diagram, it would be great if I can kind of get the rough magnitudes of these arrows correct. So the push I'm getting from this charge is from a charge that's pretty close and pretty big. Whereas the pull I'm getting from this charge is from a charge that's further away and lesser in magnitude. So both of those signs suggest that the push I'm getting from the close charge is going to be much stronger. Stronger because it's closer and stronger because it has more charge than the pull I'm getting from the far away charge. So although it's not necessary at this point, I'm going to maybe just represent that in my free body diagram by making the arrows different lengths. And let's just call these two forces F1 and F2. Okay, so let's see if we can find out the magnitudes of those two forces. Well, F1 is going to be K, Q1, Q2 over R squared. And you know what? I'm just realizing that it might be a bit confusing here because I've got a 1 over here and a 1 over here, and they don't necessarily apply to like the same object. So rather than calling these F1 and F2, I might call them FA and FB. Let's do that. That's slightly better. Okay, so K is going to be 9 times 10 to the 9. Now this force over here is coming from the interaction between these two charges. So that's going to be my Q1 and my Q2. Again, it doesn't matter which is which. R is the distance between them, 0.02, and that has to be squared. So that gives me that FA, this force to the left over here, is 95.625 newtons. And again, a reminder, remember we wrote this note on the previous page, that the formula doesn't tell us the direction. We have to find the direction on our own. So we've kind of done that down here. I found the direction on my own first. We figured out this force was going to be going to the left based on the polarities of these two charges before we did any calculations. And then once we found that direction, we went to the formula to tell us the magnitude. So the formula tells me it's 95.6 newtons. And the other work I did tells me it's left. Let's look at the other force, FB now. Okay, let's plug in some numbers. So again, FB is going to be caused by the interaction between two charges. And in this case, it was this charge and this charge. We'll call those Q1 and Q2. Now notice, when I was subbing in Q2, I ignored this negative sign. Again, that comes from the note up here. Don't use plus and minus signs. The plus and minus signs do not affect the magnitude of the force at all. They only affect the direction. I used the fact that this guy was negative already when I figured out that it was going to pull on this force. and that was conveyed in my free body diagram down here. So I've already used the fact that that's negative. Now I'm just working on the magnitude of this charge. So I use the polarity to find the direction, and now I'm going to use the magnitude, not the polarity, to find the magnitude of the force. Okay, so let's finish this off. R is the distance between them, so 0.035, and it's going to be squared. So the magnitude of force B is 24.980 newtons. And again, this is just the magnitude. This equation can only tell me the magnitude, no vector hat there. The direction I have already found using the polarity, and I drew that up here. So let's look back at what the question was actually asking us. It wants to know what the net electric force is on this charge here, the one I drew in my free body diagram. So the net force means I'm going to have to take these two and add them together. So let's do that back up here near the start of the problem. The net force, this formula does have a vector hat in it, meaning I am going to use positive and negatives here, as the formula will not only tell me the magnitude, this formula is capable of telling me the direction. This formula is not capable of telling me directions. This formula is. So FB is in the positive direction. FA is in the negative direction. So that means I have positive 24.980 minus 95.625. And that gives me negative 70.6 newtons, or better yet, 70.6 newtons left. So, quick recap on some key ideas from this problem. Units, metric base units for charge are coulombs, and then for distance, it's meters as you're used to. For force, it's newtons as you're used to. So as long as you stick with those units, you'll always end up with a familiar metric base unit coming out of the equation. And then just this reminder that this new formula, Coulomb's law, the way I want you guys to use it is only for magnitudes. If I wanted you to use the formula to tell the direction, I would have put a vector hat on it. Would have put a vector hat up here. I didn't. So just use this one for magnitudes. Figure out the direction on your own. And the way you use the direction, or the way you find the direction, is by looking at the polarity of the charge. If the charges have opposite polarity, they attract. If the charges have the same polarity, or if they're like charges, they will repel. That's all for this lesson. Hopefully that gives you enough tools in your toolbox to start solving some electrostatics problems.